So this was quiz 5. It was on timing analysis. There was just 5 questions on it. So the first question said, consider the circuit below. Consider the following table of propagation delays. And the question was critical path delay, right? Yeah, what's the propagation delay of the circuit above? Or another, I should have asked, what's the critical path delay? When you're calculating propagation delay, you want to look at worst case propagation delay. So this circuit has no fan-outs in it, meaning that all of the gate outputs only connect to one input, except for this one, which connects to 2 inputs on the same gate. So this is an easy circuit to analyze because you basically just have one path for each input to the output. You guys with me? So in other words, if we had some branches in there, it might have been more complicated, but this is a pretty easy one. The problem is, though, is that all these gates have different delays. So you may need to calculate multiple possible delays, although you can see that D and E there's no way that D and E are on the critical path, right? Because D skips over a gate that A, B, and C goes through. Likewise, E skips over a gate that F and G go through. So it looks like we really just have to calculate, and then the path from A, B, and C to Y are all the same, and the path from F and G to Y are the same. So I think there's only 2 delays we need to calculate here, right? Everyone agree with that? That makes sense? Okay, so we've got a 3-input NAND, so that's 30. So I'm looking at the top branch from A, B, and C. Then we have a 2-input NAND. NAND, no, they're NAND. Yep, yeah, 2-input NAND, so that's plus 20. And then we've got a 2-input NOR, which is 30. And a 2-input NAND, which is 2-input NAND, 20, right? So that would be 50 plus 50, 100 picoseconds. So 100 picoseconds in the top path. That would be from A or B or C to Y. And then the bottom path from F or G to Y would be a 2-input. We go through a 2-input AND, which is 30. 2-input NOR, which is 30. Another 2-input NOR, which is another 30. And finally, the 2-input NAND, which is 20, right? So that's 60, 90, 110. So we're going to take the max of these 2 values, so it should be 110, right? If I did that right. So I think that's right. Your system is running at 1 gigahertz, and you use sampling flip-flops with tau equals 100 picoseconds. T0 is 110 picoseconds. T setup equals 70 picoseconds. The synchronizer received a new asynchronous input on average 0.25 times per second once every 4 seconds. What is the mean time between failure? So this one, we got to go back and look at the equation for that. That would be under timing analysis. Okay, so it's 1 over, the mean time between failures is the reciprocal of the probability of failure per second. So I'll just say mean time between failures is TC, T sub C over N times T sub 0 and E to the TC, that's the clock period, minus T setup over tau, right? Make sense? So this is going to be TC, which is TC is, well, it's a gigahertz, so what's TC? Anyone know? So 1 divided by a billion, 1/1000th of a second is 1 picosecond, right? all right? So 1 picosecond, so that would be 1 e to the -9th, right? And then n is the number of times per second we're toggling, so it would be 0.25. And then t sub 0 is 110 pico. And this would be times e to the 1e -9 minus t setup, which is 70 picoseconds. 70e -9 negative. Sorry, that would be, I got that flipped. T sub c minus t setup. T setup 70 picoseconds. Do I have that flipped? T sub c minus t setup. Oh, no, that's right. Right. Yeah, it's a negative value. And then that's divided by tau, which is the technology parameter, which in this case is 100 picoseconds. So 100 e -9. Make sense? We just compute that. And what was the answer for this? 110 hours. Make sense? Everyone agree? Okay. All right, next question. Consider the circuit and timing parameters below. Assuming the clock runs at 4 gigahertz, how much clock skew can the circuit tolerate? Okay, so for this one's kind of tricky because the clock skew comes into play for the setup and the hold time, right? So the setup time is constraining the maximum delay through the circuit, right? So the delay is going to be, you have to add together the delay of the propagation delay of these flip-flops here, right? Which is t pcq, so that's 30 picoseconds. So 30 picoseconds plus the delay of the data path, which is between the two circuits, between the two sets of flip-flops, right? So that would be, the critical path delay would be through 3 gates. And in this case, the propagation delay of each gate is 15 picoseconds. So it would be 3 times 15 picoseconds. Okay, so that's the delay we have coming out of here and through here. Plus we have the setup time because we have to arrive before the clock edge. The amount of time before the clock edge that we have to arrive is the setup time, right? You guys with me? So it's like an extra margin you have to build into the delay. So you have to add t setup, which is, sorry, that's given to us. What's t setup? 10 picoseconds? Yep, 10 picoseconds, right? Okay, and then you have to account for the clock skew, right? So you have to potentially add the skew, which is an unknown here. Sorry, skew. Okay, so this is the delay of the flip-flops. So this is T, PC, what is it? PCD, PCQ, PCQ, right? This is the propagation delay of the logic. This is the setup time, right? And this is the skew, right? And all of this has to be less than or equal to the clock period, right? And the clock is 4 gigahertz, so the clock period is 250 picoseconds. Oh, wait a minute, I screwed that up. Gigahertz is a nanosecond, right? Yeah, sorry, I had that wrong in the last question. So yeah, 4 gigahertz would be 250 picoseconds, right? Sorry, I had that screwed up. So 250 picoseconds is our period, right? Sorry about that. Make sense? So basically, we just have to solve for skew here. So we have to so out of this 250, we have to take out 30, 45, and 10, right? So 30, 45, 10, right? And because 3 times 15 is 45, right? So the skew must be less than or equal to, this would be 75, 85, so 250 minus 85 is 5, 4, 6, 165 picoseconds. Make sense? Oh, I'm wrong there. Where did I screw up? 30, right, plus 45. So this is 30 plus 45 plus 10. 30, right? So 4 gigahertz. Am I wrong about that? Is it 4 gigahertz? Yeah, so the clock period, so you have to, again, you have to fit all of this in the clock, right? We have to be able to fit in 30, see, each gate is, propagation delay gate is 15, right? And there's 3 gates we go through. The T PCQ is 30. Setup time is 10, right? And we've got the skew is added to that, right? And the clock is 4 gigahertz. So 4 gigahertz, 250, right? So 50 skew 30 plus 45, 155. Well, let me make sure I got the equation right. So in our timing analysis, we have, oh, sorry, I know it's wrong. Actually, that's actually correct, except this is only for our setup time, right? Now we have to consider the hold time too. Yeah, that's the, so 165 would be our max skew for setup time, right? But then we have to consider the hold time separately. So for that, we will consider the hold time. So the hold time, we have to consider the contamination delay, which is the minimum time for the circuit. So that would be T CCQ, which is going to be this. So this is setup, and then hold. So we have the contamination delay of the flip-flops, which is TCQ, which is, or TCCQ, which is 20 picoseconds, plus the contamination delay per gate. Now in this case, we have to consider the shortest path, which would be 1 gate, with a contamination delay of 10 picoseconds. Okay, and then the setup time, I'm sorry, the hold time is 30, right? So we have to make sure that that these guys minus the skew is greater than the T setup time, or sorry, T hold time rather, which is 30. Okay, so the earliest we can get something through this circuit is really 30, right? But because of the skew, the inputs into the data path may get a head start. They may actually start earlier than normal, right, because of the skew. That's why we have to subtract the skew. We subtract the skew here in case we get a head start and get there early. We add the skew on this side, though, because, you know, we may get delayed by the skew, right? So this is a delay skew. And this over here is a head start skew, because you have to consider that the skew may delay you in the case of setup time, but it may give you a head start in the case of hold time. So you have to consider the worst case scenario with the skew, because the skew is a plus or minus difference in clock phases. So this is 30 picoseconds minus skew must be greater than 30 picoseconds, which means the skew minus skew must be greater than 0, right? Which means that skew must be less than 0, which means it can't tolerate any skew, right? For the hold time, right? All right, let me make sure I got that right. The answer is none, yeah. Okay, makes sense? So we were fine with skew on, we could tolerate up to 165 picoseconds of skew on setup, but we couldn't tolerate any skew on hold time. All right, next question. You're designing a 2-bit adder from 2 full adders. The adder has input and output registers. and must complete addition in one clock cycle designed for the adder as shown below. So this is basically the same kind of question as before. The idea here is that we're putting an adder in here, and really the only difference between this question and the previous question is calculating the contamination and propagation delay through this guy. So with the adder, you've got two full adders, right? Because it's a 2-bit adder. And the worst case delay for this adder is basically the carry in coming in the first adder and propagating out that first adder into the second adder and then coming out through the sum. So carry in to carry out is 20 picoseconds, carry in to S is 20 picoseconds. And so that's your, oh, and then A and B to carry out is 25 picoseconds. So if we're looking at A and B to carry out, but the, oh, and this is on each full adder. So you have to consider these separately. So the critical path here would be carry in to carry out on this guy, right, would be 20 picoseconds. And then for the second adder, it would be carry in to sum. So the full propagation delay from carry in to sum 0 would be 40, right? You'd have to add these two guys. You see that? Right, because you got to propagate from carry in through this adder, into this adder, and then out through sum. And apparently, according to this figure, unless it got cut off, now according to that figure, we're not putting carry out into the output register here. So we don't really care about the delay for carry out, this second carry out. You guys with me? Make sense? We only care about carry in, the first carry in through S0. And then for the contamination delay, the fastest we'll get a change is going to be A and B to either output or C in to either output. So I'm guessing C in to S on this first adder is going to be 15. So contamination delay is going to be 15 and propagation delay will be 40. But of course, that's just the logic in between. You have to also add the propagation and the contamination delay, or consider the propagation and contamination delay of the flip-flops as well. And then you just do the same calculation I did for the previous one. And in this case, we're just calculating max clock skew, but make sure you calculate it for both setup and hold time. Don't make the same mistake I did. And then consider the circuit and timing parameters below. Assume the clock speed is 1 gigahertz. Does the circuit meet the hold constraint? Why or why not? Why or why not? Okay, so this is just asking about hold constraint. So the hold constraint is going to be, for this guy, contamination delay for the flip-flops is 5 picoseconds. And the contamination delay for this circuit is going to be, essentially you have to add the contamination delay of 2 of those gates. The or actually the and the or, right? So that would be 20 and 25 and 30. Right? I don't see any knots in there. So it's 25 plus 30, 25 picoseconds plus 30 picoseconds. And then you have to add, actually subtract the skew. And that has to be greater than the hold time, which is 50 picoseconds. Okay, now again, there's no clock period in here. We don't care about the clock period like we do with setup. So the clock edge comes and we have a race through the logic, and the soonest we'll get a change on the output would be basically 60 picoseconds. But the skew may give it a head start, so we have to consider the worst case for skew, so we subtract skew, and that has to be greater than 50 picoseconds. Okay, so minus skew must be greater than negative 10 picoseconds, so skew must be less than 10 picoseconds. Okay? This circuit holds So does this circuit meet the hold constraint? Oh, clock skew. Sorry, clock skew is, we have the clock skew. It was 10, right? So, yeah, so we're good. Like clock skew was 10, right? 10 picoseconds, 10 picoseconds, and yeah, 10 picoseconds. But 10 picoseconds, it should be strictly less than though. So I think actually, if we're right at 10, right, because this is a strict less than, right? Let me make sure I got that right. Yeah. Yeah, so actually I think the answer is no there. So yeah, it holds for, we're going to add up these guys. 5, that would be 5, 25 is 30, plus 30 is 60, plus 10 is 70. So what do we have? What is the answer there? I'm sorry, not 70, it's 60, right? Subtract 10. So answer is no, the circuit holds for 50, right? Well, 50 is actually, no, actually 30, 50 plus 5 plus 25 is 30 plus 30 is 60. So did I get that one? Is that answer wrong? Did I screw that up? So 2 input NAND, so it's 25 plus 30. Did I get the short path? No, the short path looks good because all of these paths go through both of these guys. So it would be, yeah, it would be, well, I guess 25 plus 30, 55, but that's the contamination delay of the circuit. And plus then you'd have to add the 5 from the flip-flop. So that gets you up to 60. But then you subtract 10 and that gets you down to 50. So I guess, yeah, so is it the 50? Was that the answer? Yeah, 50, right, okay. So basically, yeah, we just added up this side of the inequality, and this is 50, right? 50 picoseconds. Minus 10, right, okay. So the answer is no, but it's close because the idea is that you have to be less than the hold or less than the hold, right? You guys with me? Okay, alrighty. Okay, so last lecture we were talking about these digital building blocks, and I reviewed the ripple carry adder. And the ripple carry adder is when you create a chain of adders for each column of a multi-bit addition, right? So these are columns. Each column is the corresponding bit position between two multi-bit values that you're adding together. And then the carries, a carry from one column, a carry out from one column flows into the carry in of the next column, right? The problem with this is that it's slow because the propagation delay is n times the propagation delay of a single full adder, right? So it's n times the time for a full adder, where t sub fa is the propagation delay for a full adder. So a faster way to do this is using a carry-lookahead adder, and the goal here is to be able to break that long chain of carries. And the way you do that is you generate a signal called propagate and a signal called generate from each of the full adders. And then you can figure out, or you can infer what the carry-in is into each column from the propagate and the generate signals from the previous columns. You guys with me? Right? So the way you do that is you basically look at the, hold on a second, wrong slide. So you look at the generate from the column before you, right? The column before you, if it generates, then your carry-in will be 1. Or if the column before you propagates and its carry-in is 1, then you also have a carry-in. But then you can replace the carry-in from column I minus 1 with this same expression, right, and build it up. So basically, well, these are, hold on a second, these are for blocks. Where's our okay, so hold on. So for a single column, right, the carry-in on column I is going to be the generate on column I minus 1, right? Or a propagate on I minus 1, and then ANDed with the carry-in on I minus 2. Make sense? Okay? But we want to get rid of these carries, right? So you can replace this with the generate on I minus 2 plus the propagate on I minus 2, ANDed with the carry of I minus 2, carry-in of I minus 2. Right? And you could keep building this out. You can continue building that out. The problem is that as you make this expression larger and larger in order to calculate carries of bits further to the left, you end up with this enormous logic circuit. It's not very scalable because you end up with a lot of inputs. You end up with a Boolean expression with P's and G, a lot of different P's and G's from all the prior columns, right? Now, in principle, you could do that with just a 2 levels of logic, right? A product of sums, right? But the problem is that expression is going to get big because you're going to end up with a lot of inputs to the gates in there, a lot of inputs to particularly the sum, the OR gate at the end. You guys with me? Right? It's not scalable. Basically, the only way you can really do that is on a small group of bits, right? But you can extend this method and make it hierarchical. So the idea, and this is generally how these are built, is you can calculate the generate and propagates on groups of bits. So in this case, this is the generate and the propagate corresponding to a group of columns 3 down to 0, right? So what I showed over here, these were individual bits. So, like, let me give you a concrete example for a block. So if I have a 4-bit adder, the carry-in for 3, right, is going to be the generate for 2, or the propagate for 2, and the generate for 1, or the propagate for 1 and the generate for 0, right? Or the propagate for 0 and the carry-in for 0. Right? Does that make sense? Right? So the carry-in 3 is going to be the generate on 2 plus the propagate on 2, generate of 1 plus propagate of 1 plus propagate of 1, propagate of 0, carry-in of 0. Or we can expand this. Carry-in 3 equals generate 2 plus propagate 2, generate 1 plus propagate 2, propagate 1. Sorry, it was propagate 1, let's see, propagate 1, generate 0. There we go. So propagate 1, propagate 2, propagate 1, generate 0 plus propagate 1, propagate 0, carry in 0. And that would be a 2, actually, propagate 2. Okay? So if you look at this, it makes sense. So the carry in for bit 3 is going to be the generate of bit 2, right? Or the generate of bit 1 combined ANDed with the propagate of bit 2, or the generate of 0 ANDed with the propagate of 1, propagate of 2, or the carry in of 0, because we have to have an original, this is the original carry in from the user perspective, ANDed with propagate 0, propagate 1, propagate 2, and that's it, right? Yeah, because then that would have propagated into bit 3. Guys, okay? Makes sense? So the first, basically the pattern here is that you start with the generate, or you end with the generate, and you start counting down from 3, right? Any questions? That makes sense? So you could continue building this up, but the problem is that if you look at this expression, to put this into logic, you could have like, you'd have to have an OR gate that's 1, 2, 3, 4 inputs, and then you have to have an AND gate here that's 1, 2, 3, 4 inputs, right? And as you start putting these, it becomes impractical to make these single gates with a lot of inputs. So if you were to run this through the synthesizer like Quartus, it'll actually decompose these big gates into smaller gates. But what you will end up with is a slow circuit, right? So what's done instead is you still do this for small blocks, but instead of scaling up all the way to a 32-bit adder, you can calculate the generate and the propagate for a whole group of bits. So you can see the generates bit 3 down to 0 is can be computed from the generates basically all the way across that block of bits. So the most significant generate, notice that there's a single subscript here. So generate 3 or propagate 3 and generate 2, or propagate 2 and generate 1, or propagate 1 and generate 0. So this will generate, the first expression will give you a top level generate coming out of the group of 4 bits. And then the bottom expression will likewise do the same for propagate. So this allows you to propagate all the way through, a carry all the way through a group of 4 bits, right? Okay, so so this way you can calculate the carry in to I, which for example might be say 8, right, bit 8. And you could calculate that from the generate of bits 7 down to 0, right? Or the propagate 7 down to 0 and the carry going down to this would be, in this case, in this example, would be the original carry, right? Carry -1, right? The carry coming into the group. You guys with me? All right. Okay, so we can calculate, so the generates and propagates of individual bits come out of each full adder. They're used to generate carries into all 4 bits of a block of adder, and then you generate these top level propagate and generate bits that are used to basically generate the carry-ins for each group of, or each block of bits, each block of columns. Okay, so what is the delay of this? Basically, the idea is you've got, in this case, we're going to separate the adder. It's a 32-bit adder, and we're going to decompose it into 4-bit carry-lookahead blocks. So the propagation delay would be the time it takes to generate all the PGs, propagates and generates. Now that's just a one-time cost though, because all of those things are being generated concurrently from all those blocks, right? From all the individual bits, because this is P sub I, G sub I, right? So the propagation begins with that, and then once you have the individual bits, P and G, you can calculate an additional layer of logic for generating the block level propagate and generates. Okay, so because, and that would be just using this type of expression, right? Where you're taking the individual bit, the individual column PNGs, and you're combining them to create block level PNGs, right? Okay. Now, that's just a layer of logic that sits on top of the bit level PNGs. So the signals come out of the inputs, they go through the full adders, you get bit level PNGs, those flow into another block that gives you the block level PNGs. Okay, and then once you have that, then you can calculate, in this case, we're going to calculate the carry out from each one of those blocks. And the carry out from each one of those blocks would be essentially just the expression for this expression, right? So we need to have the top level carry. The carry out would be the generate from the block plus the propagate of the block and the previous carry in, right? So the problem here is, the problem with this is that what that means is to calculate the carry out, we need the carry in from the previous block, right? So now we have basically another ripple effect that's happening here, because we can calculate the P's and G's and the P's and G blocks in parallel, concurrently. But then, once we have those, now we have to generate carries from each block, and those carries have to flow through each block, right? Now, the good news is, though, is that the delay from the carry in to the out of the carry out is only 2 gate delays, right? And the reason for that is because of what you end up having to do is just basically calculate that last expression. So you have the carry in from the previous block, you AND it to the propagate, right? But see, the idea here is that this propagate, this gets a head start, right? So you can start, the logic can start propagating this value, right away. The carry in is basically just at the back end where you AND it with the propagate from the previous block, and then you OR it with the generate from the previous block, right? And the generate from the previous block, it doesn't depend on the carry, right? So the only thing that depends on the carry is this right here at the end. So what you end up doing is you take the time it takes to do this AND OR thing, right? And you have to multiply that by n divided by k minus 1. Because n is the total number of bits and k is the block size. So if this is a 32-bit adder and you have 4-bit blocks, you're going to have to go through 7 of these guys, right? The original one you get for free, because when you set the inputs to this adder, you're going to give it the carry in. But then you have to generate 7 of these intermediate carries between the blocks, and each one of those has to go through this AND OR. So that's why you have to multiply n divided by k minus 1 times t AND OR. And then you add the full adder to that, because once you've generated all the carries, you have to then actually do the add, right? But again, that in the k, and the reason why it's k is because the k, of course, is the block, and once you get the carry in coming in here, you have to still like ripple carry that carry in through the 4 bits, right? And so you can't do that until you've got all the carry outs, right? So that's why we have to add n divided by k minus 1 of this AND OR, and then you have to add the final ripple carry through the 4-bit block. Make sense? You guys with me? Okay. So what is the point? The point is that this carry lookahead adder, it still gets slower as you increase the size of the adder, but you're essentially dividing the performance, or the delay has these 3 fixed terms, right? This term, and this term are fixed, The only one that scales up with the size of the adder, I mean, assuming a fixed k, is this n, right? So if you go from a 32-bit adder to a 64-bit adder, you're going to it's just affecting this one term, and you're going to end up increasing the coefficient there by, by another 32 divided by 4, right? 8. Make sense? So it scales better than a ripple carry adder. Okay, so the final type of adder is the prefix adder, and this one's kind of neat. The idea with this, it's kind of similar to the carry-lookahead. You still have these propagates and generates. The difference is that with the carry-lookahead adder, these generates and propagates were always calculated in fixed blocks. So 3 down to 0, P and G 3 down to 0, right? And then you also would have, this block would give you P and G 7 down to 4, right? And then you'd have P and G 11 down to 8, right? So you would always have these 4 column chunks for P and G. With the prefix adder, they don't have that same restriction. With the prefix adder, they calculate generates and propagates with arbitrary ranges of bits. And also, they consider column -1, or I should say the generate -1, just to be the top level carry in, right? By convention, okay? So the idea is that you can build up these blocks by combining together 2 other blocks. So if you have a range of bits, I down to j, that you want to calculate the propagate or generate for, you can build it up from another set of 2 sets of bits, which would be I down to k and k minus 1 down to j, right? So it's G I down to j and P I down to j, but G I down to j can be built up from G I down to k and G k minus 1 down to j. Does that make sense? You guys with me? So basically, you're calculating the propagate and generate for a range of bits by combining together 2 other blocks, right, that are both adjacent to one another. Does that make sense? Okay, so essentially, what you can do is that you can calculate the idea is we want to have the propagate and generate of, well, let's start on the right-hand side. The propagate and generate of 2 down to 1, right? Now we can calculate that as a function of the propagate and generate of the individual 2 and 1, right? So 2 down to 2 and 1 down to 2. You put those together to get 2 down to 1. So the way that works is, the way that you comprise these is, if you have, now by the way, keep in mind that when I say like P I down to j, this is a wire. This is basically a value, a Boolean value that you're calculating, right? It's just a wire. So, you have these indexes, but this is not to imply that this is like an array or something. It's just a wire, right? So if you have P and G of single bits P and G, you can combine them together to get a 2-bit PNG. But you do it for each pair of inputs. So you have, and the way you set this up is you start with 0, PNG 0, and PNG -1, right? And then you have PNG 2, PNG 1, right? Now remember, with the full adder gives you PNG, it's part of the full adder architecture, right? Remember we added that. We added the single bit PNGs. So each one of these black boxes here is going to combine the two separate groups into one group. And basically all you have to do for that is the propagates are just ANDed together, right? So I AND together the propagate, for example, from bit 6 and 5, right? To get to the propagate for 6 down to 5, right? And likewise, the generate for bit 6 down to 5 is the generate for 6 and the generate for, the propagate from 6 ANDed with the generate for 5, ORed with the generate for 6, right? So you combine them just with these, basically just these 3 gates. Okay? And then once you go through that first level, then you have P and Gs for just pairs of bits, right? 14 down to 13, 12 down to 11, 9 down to 10, 8 down to 7, right? And then you take each one of those pairs and you can combine them together, right? But you're not necessarily just putting pairs together, because you can also do stuff like this. You can do arbitrary things, like you can take 6 down to 5. So this guy takes 6 down to 5, which is 2 bits, and then he's going to grab 4 down to 3 and combine those to get 6 down to 3. Okay, so that makes sense. Those are just 2 consecutive pairs. But over here, check this out. You can get generate and propagate just of bit 5, right? Just a lone bit. But then you can combine it with 4 down to 3. So now I have 5 down to 3. That's 3 bits, right? Because you might say, well, wait a minute. You group together every pair, and then you're going to put those pairs together, so you're going to have groups of 4. Then you're going to put those groups together, and you're going to have groups of 8. But it doesn't work like that, because you can join arbitrary. You could take a group of 2 and combine it with a group of 1 and to get a group of 3 bits, right? Or, like for example, you can take, over here I've got bit 11 by itself, and I'm going to combine that with groups 10 down to 7 to give me 11 down to 7, right? So I'm going to take a single bit and I'm going to combine it with 10 down to 7, which is 4 bits, to get this 5-bit range of 11 down to 7, right? So you can build these groups up in an arbitrary way. It's not just putting pairs and quads and together. You're putting these arbitrary pairs. What you end up with is, by the time you get to the bottom, what your goal is you want to be able to calculate the carry-in to each individual column, which is when you have a group that is that number, the column number, all the way down to -1, right? Right, does it make sense? So, like for example, here, the carry-in for column 9 is basically the generate from 8 down to -1, right? All the previous bits, right? So all of the final bits have their own individualized carry-in that is calculated from a combination of groups, that eventually your goal is to get the final bit output bit column down to -1, right? And that'll just be its carry-in. You guys with me? Okay, so what this figure shows is that this picture right here shows, this is just A sub I, B sub I, P I to I, G to I. So this is a single bit P and G. This is a single bit right here, right? And then this is how you combine a P and a G that you have I to K, and then K minus 1 to J. So this is going to give you I to J, right? Because it's I down to K, then K minus 1 down to J. You combine those together and you get I down to J. And so you just have to go through 2 gate delays to get that, right? It's a very simple, it's a very fast way to generate those. Okay, and then if you have the generate, I minus 1 down to -1, right? Then you just treat that as the carry-in, and then you just do the XOR thing to get the actual bit out, right? Now you might say, whoa, what about propagate I minus 1 down to 0? Do I need that? No. You just ignore that. So by the time you get down here, all you care about is the generate bit. You don't even care about, on the last level, once you get down to this last group of boxes, all you care about is the generate coming into here. You actually should ignore the propagate, right? But once you have the generate, that becomes your carry-in, okay? So what ends up happening here is that the time for this guy is the time to calculate the initial propagate and generates, this little circuit, right? Plus log base 2 n, where n is the number of bits. So if it's a 32-bit adder, there's only 5 stages you go through. This is a 16-bit adder, so there's 4 stages. You can see the 4 stages of boxes. So log base 2 times n, and you're multiplying that by this prefix, this thing, this circuit, which again is just basically 2 gate delays, right? And then you have to add the XOR, which is once you have the generate into U, you just use that as your 3rd bit to add up to get the sum, right? So this adder scales up as a log base 2 of the number of bits. So what ends up happening is that if you're comparing this to, if you're comparing the ripple carry, the carry look ahead, and the prefix adder, the prefix adder is going to be the fastest one, assuming that the circuit is big enough, I think. I think if your n is small enough, the carry look ahead may win. But in general, for a large enough adder, the prefix adder is going to win. In this case, for this set of parameters, the ripple carry, this was a 32-bit ripple carry look ahead and prefix. We're using 4-bit blocks for carry look ahead. 2 input gate delay, 100 picoseconds. Full adder delay is 300 picoseconds. And you end up with 9.6 nanoseconds for the ripple carry, 3.4 for the carry look ahead, and 1.2 for the prefix. So the prefix does really well there. Make sense? Okay. All right, so those are the only adders we're going to cover. Subtractor, how do you make a subtractor? You just use an adder, but you negate the second input B, and the way you negate it is use 2's complement. So you complement all the bits of B, right? But you can't have another, like remember 2's complement, you complement and add 1, right? Well, you don't want to have a separate adder to add 1, so the way you can hack around that is you just use the carry in, right? So if you negate B and you set the carry in to 1, that negates B and you get a free add 1 there, right? So that's the way you convert an adder into a subtractor. How about comparing two signals? Well, this is what the book says to do. The book says that you can do an XOR gate between each pair of bits when you're comparing for equality, and then you route all the outputs of those into a big AND gate. But that's one way to do it. The problem with that, though, is that this AND gate is going to be really big. It's going to have a lot of inputs, which, again, like I said, it'll get broken into smaller gates when you synthesize it. But another way to do this would be the way we do it in class, which is to subtract A and B. Of course, even then, you have to technically, after you subtract it, you got to put all the output bits into an OR gate to make sure they're all 0. So this architecture might not be that bad. Okay. Less than. If you want to know if if A is less than B, how do you do that? Well, you can subtract, right? And in this case, they look at the sign bit. So if A and B are both 0 or positive, they're going to have a 0 sign bit. And if you subtract them and you get negative, you get a negative difference, then A is less than B, right? But what happens if they're both negative? If they're both negative and you subtract, right? Then it's the same idea. Like say A is -10 and B is -5, right? And we subtract them and we're going to get -5, right? Well, that means A was still less than B if the sign bit is set, right? Okay. How about shifters? So shifters are actually can be more expensive than you might expect. So a shifter, there's really two ways you can build a shifter. The one way is you can shift 1 bit at a time, right? So 1 bit, if you're shifting 1 bit at a time, you can just connect flip-flops in series, right? But if you want to be able to shift by an arbitrary amount, that's called a barrel shifter. I don't know how it got that name. But a barrel shifter is fundamentally, and this isn't necessarily how you implement it, but you could think of it as having your inputs come in, and you have a series of muxes for each output bit, right? And each mux is going to accept all of the input bits, right? So if it's a 32-bit shifter, you'd have 32 muxes, right? You would have to be able to. The idea is that you'll set the muxes up to perform the shift. So in this case, this is a 4-bit shifter, and so if we don't want to shift at all, then you would set the muxes to 0, in which case this guy is going to get A3, this guy's going to get A2, this guy's going to get A1, and this guy's going to get A0, right? It's going to just route. Wait, where's it? Yeah, A0 is right there. There's a connection right there, right? If you set the mux to 1, then Y3 is going to be a 0, right? Because that's ground, right? But Y2 is going to get A3. You see that? So A3 is shifted down one position to Y2, right? And likewise, Y1 is going to get A2, and Y0 is going to get A1, right? And A0 goes nowhere. It gets shifted off, right? So A0 gets shifted off, and Y3 is going to get a 0, right? So what's happening here is that this shifter is basically shifting from, let's see, which way are we going here? So if our shift amount is 1, Y3, which is the most significant bit, is going to get a 0, right? Which means this is a right shift, right? Because when you shift right, you're going to shift off the least significant bit, which in this case is A0. So A0 goes nowhere, right? If we shift by 1 or more, right? Gets shifted off. And the most significant output bit, which is Y3, is going to get, that's going to get a 0. And the least significant bit, Y0, is going to get, it's going to get A1 if you shift by 1, A2 if you shift by 2, or A3 if you shift by 3. Make sense? You guys with me? So it's expensive, right? I mean, you can imagine if this is 32 bits, this is only one direction too. This is not a left-right shifter. It's just a right shifter, right? Okay, and as I mentioned, you can also build something called a shift register, which is where if you connect flip-flops in series, then every clock you're going to shift one value, right? You're going to shift, each value will travel from one flip-flop down to the next, right? Now you might say, wait a second, hold on. How is this working with hold time, right? Because once you hit the clock, this delay between these two guys is negligible, right? That's going to violate the hold time constraint, which is true, but remember the CAD tool will automatically put delays in there to fix that, right? So you don't have to worry about that. If you build a shift register like this in Verilog, the CAD tools will take care of the hold time constraint resulting from there being no delay between these guys, right? So what will happen is that values will get shifted in with SN and then they'll shift it out with Q. This is also a serial to parallel converter because we're shifting one bit at a time and we're reading the outputs in parallel from all the registers, right? All the flip-flops, right? And then you can extend this by adding a parallel load. So you can have a D input, which is in parallel, and a Q output, which is all in parallel. And then you can use a mux before each flip-flop to load in the Ds in parallel. So you can initialize this guy in one cycle, and then if you switch these muxes to 0, it'll then start shifting one bit every clock cycle. But again, this is shifting one bit every clock cycle, whereas the previous shifter I showed you allowed you to shift an arbitrary number of bits, right? But this one, if you want to shift 7 bits, you'd have to wait for 7 clock cycles to do it, right? Okay, and then we talked about I think we talked about this earlier, which is using shifters for divide and multiply. So if you shift to the left, you're actually multiplying the value by 2 to the power of the number of bits you shifted left, right? And if you shift to the right, you're dividing by 2 to the power of the number of bits you shifted to the right. The problem with that is that it's limited to powers of 2, right? So what happens if I don't want to multiply or divide by a power of 2? Well, for that, you have to think about how you would set that up. So remember, when you do grade school multiplication, you have the multiplicand and the multiplier, which can be, multiplication is commutative. You can switch whichever one. But one of the numbers is the multiplicand and one's the multiplier. And you're going to take the multiplicand and multiply it by each digit of the multiplier, right? And then you're going to add up all the products, but each product is going to be shifted by 1 digit, right? According to which digit of the multiplier you multiplied by, right? And you just add them up, right? So that's in decimals. And in binary, it's a little bit easier because basically all you're doing in binary is you're looking at the bits of the multiplier, and for each bit that's 1 in the multiplier, you're just adding 1 copy of the multiplicand. You don't have to actually change it like you do over here in base 10, right? You're just saying you're going to take the multiplicand, and for each bit that's set to 1 in the multiplier, you just add, right? Except you add a shifted version of the multiplicand where it's shifted by the corresponding 1 bit. So basically, if you're multiplying by 7, you take the multiplicand and you add it, you shift it by 1, which multiplies it by 2, and you add it, and you shift it by 2, which multiplies it by 4, and you add it. So you have a by 4, a by 2, and a by 1, right? And when you add all those up, it's 7, right? You've multiplied it by 7. So basically, all a multiplier is in binary is just a shift adder, right? All you do is you look at each bit of the multiplier, and for each bit that's set 1, you just add a copy of the multiplicand shifted that amount, right? So that multiplier is fairly simple. The problem is that it's expensive because you have to have 1 adder for every bit in the multiplier, right? So that's an issue. It makes multipliers expensive. So here's an example of one. So this one, the shifting is performed by basically you've got your A, which is your multiplicand, and B, which is your multiplier, right? So you've got A here and you've got B on the bottom. And so what you're doing is you're taking B and you're putting B into AND gates, right? And those AND gates are basically turning off each bit of B, right? Each bit of B is going into an AND gate. They're turning off the multiplicand if the corresponding bit in B is off, right? Does it make sense? So you end up having this thing where this first layer is these are full adders, by the way. So these are just single bit adders. So this is building a multiplier from single bit adders. And so you have, for the least significant one, you just have basically just B0 and A0, right? Because if you look over here, right, the least significant bit of the product, right, is literally just A0 ANDed with B0, right? So that's this guy, right? And then the next significant bit is, the next most significant bit of the product, P1, is we have to AND A1 B0 and A0 B1, right? So you can see that those are the two AND gates there, and they feed into a single bit adder. Now the problem, notice though that the carry out is, you've got carry out chains that are at each level, right? So this guy could generate a carry. Obviously this guy can't generate a carry because he's just an AND gate. But this guy can generate a carry, so you have to worry about that. But then when you get to the third column now, you have two adds. So you've got your two adds here, right? Which is going to be, where you're adding, you've got two adders, but you're actually adding together three things. So you've got A2, B0, A1, B0, A0, B2, right? So that would be this guy. So you might say, wait a minute, why is there two adders if you're adding three things? Well, the first adder takes care of two, and the second adder adds the third value in, right? And then you do take care of the carries at each level of the addition, right? So what ends up happening here is if you look at it, this is literally arrays of carries, right, that are being sent horizontally across all these full adders. Make sense? And then once you get to the final, the most significant bit, again, is just going to be, well, you'll have a carry out from the last adder as P7. Right? And then you've got A3, yeah. So here's A3 ANDed with B3, right? And that's ANDed, that's sent into this adder, which is accepting, the reason why we need an adder here is we need to get the carries, right? So we have a carry from the previous column. Make sense? And there's different ways there's different adder multiplier architectures. This is just kind of a simplified one. All right, what about division? So division is a little bit more complex because the problem with division is, so you've got, if you remember from grade school, you've got your dividend, which is you can think of that as like the numerator. The dividend is what you're dividing into, and then the divisor. And then you end up with a quotient, which is the basically the value, the result of the divide rounded down, and then there's a remainder, right? Whatever's left over. So normally, the way you'd handle this in like grade school is you look at the divisor and you look at the dividend and you figure out, you use kind of human intuition where you figure out where that divisor fits under the dividend, right? So we have a 4-digit divisor, and so you're going to line this up under the first 4 digits of the divisor, right? And in this case, you're going to multiply by 1 the divisor, and that will subtract basically 9 minus 8, right? But it's not 9 minus 8 because that number is bigger than 9. But 9 is the first 4 bits, right? Okay, and then you subtract 9 minus 8 and you get 1, and then you drop down a new bit from the dividend, right? The problem, though, is that you look at that and you say, well, there's only 2 digits there, and I can't actually, there's no way I could subtract the divisor, which is a 4-digit number, from a 2-digit number, right? So what do? You drop down another bit from the dividend, and you just put a 0 up there in the quotient, right? But a lot of this, the problem with this is that a lot of this is governed by you just looking at it, right? Figuring out what to do. The problem is when you're building hardware to do this, the hardware doesn't know from looking at this that 2 is too small to subtract out 8. It doesn't know that, right? So what it's going to have to do is it's going to have to try. It's going to have to say 2 minus 8, and it's going to get a negative number, -6, right? And so then it's going to have to take that and reverse it. It's going to have to go back, undo, and make that -6, turn it back into 2, and then add another digit. Well, actually, what I should have said is it starts out with 1. Yeah, starts out with 1, right? So we're going to subtract 1 minus 8. It's negative. We're going to bring a 0 down, right? And then we're going to say 2 minus 8, that's negative, so I got to bring another bit down, right? And then I'm going to say 5 minus 8, and that's negative, and I got to bring another bit down. So this is what's called a restoring divider, meaning that basically you have to subtract the divisor from a shifted form, shifted right form of the dividend. And if the result is negative, then you have to restore, undo that subtraction, shift the dividend, and try again. So when you first start out, actually, you're going to start out with a 1 here, actually, right? So you're going to have 8, and you're going to start out with just the first bit, 1. So you're going to say 1 minus 8, negative 7. Okay, I'm going to put a 0. So there's a 0 above that 1. You guys following me? Right? You just don't see it on here, but it's implied that there's a leading 0. Then you're going to look at 2. You're going to shift this to the left. And it's now 2. And I say 2 minus 8, negative. Okay, another 0 there. Shift it. Now I have 6. I'm sorry, 4 rather. Sorry, 4. 4 minus 8, negative. 0. Shift this guy. Now I have 9. 9 minus 8. Oh, finally I have a non-negative number. So I put a 1 in the quotient, and I don't restore. I just keep that 1 there, right? I keep the 1. And then actually, yeah, I was wrong. Actually, with the 1, right after you have that 1, you're going to shift and you'll have 2, right? So after you get that 1, you will add that 0 there, and then you'll have 2 minus 8. It's negative. So 0, restore, bring in another bit. So basically what you're doing is you take the dividend, you shift it to the right? You shift it to the right, and you keep trying to subtract the divisor from that partial dividend, and every time it's negative, you restore it back to the way it was and put a 0 in the quotient. Every time it's positive, then you keep the value you got from the subtract, right? But you keep shifting in bits from the dividend. Does that make sense? That's the principle of this, right? So the problem with divide is, the reason why divide is so expensive, some processors don't do hardware divide, because this is fundamentally why. With a multiplier, you basically don't have any decision logic to worry about. You don't have to check to see if something is negative, and if it is, restore it. There's no if statement. There's no check, right? There's no conditional behavior in a multiplier. But in a divider, you fundamentally have to do this kind of trial and error stuff, which is why division is really expensive. And if you can, avoid divide in your hardware, or especially in hardware design, then you'll avoid it. Like, for example, the ARM processor, the ARM v7 processor that were in all phones and tablets up until the ARM 64 came out, which was, I don't know, a few years ago, right? ARM processor didn't used to have a divide instruction. They later added one for the ARM v8, but ARM v7 didn't have a hardware divide. You had to emulate divide because it was just too expensive, and it's not used a lot. Okay, so, oh, sorry, I forgot I had an example. So basically, yeah, so here's my example, my animated example. So the hardware is going to try to, he's going to try to subtract, he's going to shift this guy over. There's just a 1 showing, right? He's going to try to subtract, and it's negative, so you're going to keep moving that over until you get to the point where you can do your subtract, at which point you put a 1 in the quotient, and then you just keep, repeating that process, right? Okay, so the architecture for this, you can build this in an array, kind of like a multiplier, but what you have to end up doing is you have to use these boxes, and these boxes have an adder, well, they have a subtractor, right? So it's an adder, but notice how B has a bar over it. So you negate B, and all of these adders have a 1 carry-in, right? So basically, this is a subtract, but then after the subtract, you have a mux, and the mux can either accept the result of the subtract, or it can pass the original remainder down, right, and basically restore, right? So this mux is deciding whether you're going to keep the result of the subtract, or you're going to basically abort the subtract and bypass this guy, right? So you have this, B is the value, your divisor, and A is the dividend, right? So you start out with, notice that you've got A3, right? A3 is A shifted all, well, it's 4 bits, so it shifted 3 bits to the right, right? So that's the first bit of A. But as you come down, you keep adding additional bits in here, and then you shift to the left the result from the previous stage. Does that make sense? Right? So A is getting shifted in one bit at a time by adding bits of A over here, and then you have these diagonal wires that shift down. Right? Does that make sense? Okay. All right, so the idea is that if you look at the outputs from each stage, the outputs from each stage of this guy are going to be essentially the remainder, all the values that you've subtracted. At the very end, you'll get the remainder out. And then the quotient will be, the quotient is going to be essentially the result of this comparison where you check to see if the result of this guy was negative. Make sense? Which is n. N is the decision. Where's the logic? Yeah, anyway. I'm just about out of time. I will finish this up, and then this is the last topic from building blocks. I haven't posted the quiz for this yet because I wasn't sure if I'd get through it. I'll probably wait on the quiz, post it next week. Next topic will be transistor level design. Okay?
Thank you.
Thank you.